Yeah, we are on live. Uh, a very good morning to all. In the outset, I would like to quote unquote Brahma Veda Amritam Prasata Brahma Pita Brahma Uttarata Dakshinastena Adhasya Daharu Sapastam Brahma Veda Vishwamidam Varishtam. This is a well-known saying from our ancient Sanskrit script, that is Mundu Upanishad, which explains the Vedic quantum understanding of the connectivity of living entities is put forward to help the individual to understand the difference between the body and the living entity. How the real quantum nature of the living entity is realized only in union with the source, the supreme being through a platform of transcendental divine loving service. The same analogy we want to extend and expect from today's lecture, where we can draw a number of insights and gateways of nuances about the quantum technology. Dear friends, on behalf of Department of Physics and Vigyan Setu Forum of Dolphin PG Institute of Biomedical and Natural Sciences, Dehradun, I, Dr. Asida Puri, welcome you all in this very much awaited distinguished lecture. Dear friends, the Gyan Setu Forum of the Institute is a committed platform working towards enhancing the qualitative temperament of science. Through this very program, we always bridge the gap between the learner and the laboratory and empower concerned individuals, thereby creating a holistic vision of innovation and motivational atmosphere. We promote a comprehensive approach to scientific development. We bring together scientists, academicians, experts, and make them share their experiences and science-based skills among the students and maths. In this continuity, today we have joined by eminent professor Mrityunjay Guha Mazumdar. Welcome, sir. Dear friends, I am very much delighted to introduce today's speaker. Dr. Mrityunjay Guha
Thank you,
Mazumdar
thank you, Doctor.
has has over a decade of experience
Thank you.
working in the area of quantum entanglement and quantum information, which began with his selection as a TIFR NIS Fellow in Physics in 2012. He did his doctorate in quantum physics in the renowned Cavendish Laboratories, Cambridge University, graduating at the age of 25, having been awarded the Trinity Bell Fellowship and Nehru Scholarship for his doctoral studies. His areas of interest has been primarily in the quantum entanglement within the across transfer degrees of freedom and its application in the domain of advanced quantum information processing system. After his doctoral studies, he went on to work with the Nobel laureate physics in 1973, Professor Brian Josephson, in the area of nonlinear physics, coordination, dynamics, emergent phenomenology. He subsequently had prestigious postdoctoral fellow at the Tata Institute of Fundamental Research, Indian Institute of Science, and Harvard University. He has published and given talks on the topics in the areas of the quantum network, coding, quantum transaction, and more recently, hyperentanglement, particularly around hyperconditional gates and the quantum random walk. He has taught undergraduate and postgraduate courses in physics in the Cambridge University and Delhi University. Respectively, he had led an international initiative in the science of evolution and the policy. He was showcased in the special program on the quantum mechanics aired on Doordarshan, India's national broadcaster, and has previously worked with the Ministry of Human Resource Development, now it's the Ministry of Education, Government of India, on the competency-based learning in education, particularly in the South. He represented the Republic of India as a youth scientist in the first Asian Youth Science Summit, with the resolution from the summit being directed to the governments of Asian countries along with India and China. Besides science and education, Dr. Duha Mazumdar has an active interest in social work, activism, and spirituality. He was showcased by the UNESCO in its Convention on Higher Education in 2018, and more recently led the drafting of the NGO UNESCO position paper on youth and advocacy that is sent to the governments of over 60 members countries of UNESCO. He is a four-time elected student leader of the Cambridge University and has worked with the various social organizations such as the Pratham, Seva Bharati, Save Child Heart, Plan International and Voluntary Health Association of India. He is a convener of Mandala Vizna Bharati and has been a member of C20 consultation for the G2023. Dear friends, I'm very delighted to welcoming the eminent professor, and you know that I sent him a message through the chat box, and he, without any delay, he just accept my invitation. It shows it's a direct connectivity and commitment for the science population in this country. Your friends, really, he's a cosmos personality of the intellectual domain of this country, and a man who has a quest to reveal the unexplored wonder of the universe through his quantum computational skills. So, without any further ado, I would like to invite Professor Guha Majumdar for his talk on quantum technology, application, and implication. And I would also request to our audience, if they have any queries, you can drop in the chat box. And I would like to request Professor Majumdar, definitely he would love to answer the same.
Sure.
So, sir, please, sir, this mic is now over to you. Please.
Yeah. Thank you, Ashishji. That was very kind of you. So today we'll be talking about this topic, which has been in the news across the world and also in India, of course, which is to do with quantum technology. To begin with quantum technology, I think the major part or the major idea or premise behind it is to look at what is quantum mechanics itself, and what is the context in which technology came to be moved into a new direction, using the power and the resources inherent in quantum physics as such. So without further ado, I would like to get into the presentation itself. And I'll be more than happy to field questions as we go along as well. You can try to put it on the chat box, and I will try to see if I can possibly answer them as we go along, right? So, okay. So let's see. Just a moment. Right. I hope this is visible, Ashishji.
Yes, I'm just putting it on stage. Then I think we will go ahead. Yes.
Okay.
Yeah,
Yeah.
it's okay.
Yeah. Yeah. So the presentation or the talk today will be on this idea of quantum technology, and the title here, as you may see, is the quirks of the quantum. Quarks is something which is unique, which is different. It's even a little outlandish in certain ways. And quarks is often given when we are breaking through from a convention of sorts. And that is exactly what happened in the world of physics when we began with this quest of sorts of exploring nature, of exploring reality at its most fundamental. So in the before the 20th century, as many of the viewers here would know, we had what was known as classical physics or classical dynamics. And my own journey in the area of physics itself began with what many of us have, which is that of curiosity, right? Which is that you see something around you, right? It could be the stars in the sky, it could be various kinds of fluid dynamics, for instance, in different kinds of systems. For me, I distinctly remember the oil slick interference patterns, right? So you must have seen that when you have oil which is laying on, let's say, a surface, there is a certain kind of interference pattern that you can see that comes from that because of the light dynamics as such. And that was something which brought me into physics, or one of the things. Of course, there are a lot of other things as well. This whole idea of this curiosity being addressed by a certain combination of parametrization as well as theorizing, which can help us in understand what is actually happening, right? So this was one thing that definitely was of note for me as an individual. And you must have all have seen this particular entity called the Zorb. The Zorb is basically this giant ball, right, where people go inside, right? And then there is this whole idea of circular mechanics and translational mechanics, for instance, rotational and translational mechanics. And friction and gravity, of course, also work on these balls as people roll around in them, right? And that also is very much part of classical mechanics. And then, of course, we have the four-stroke engine, the engines that are used in cars and various other, vehicles. We have, which is also part of classical mechanics and is part of classical thermodynamics, as many of us must be familiar with. So, at the turn of the 20th century, this was where we were standing essentially, and there were two questions that came forth. Right, the questions were that if bodies are traveling at a very high speed, right, or they are in a very minute layer of reality, what is the physics of that? Right, what happens in terms of the reality at those levels or those regimes? And that is exactly what brought about a couple of revolutions in the world of physics itself, which I'll be addressing shortly. So, but however, having said that, just before the 20th century, there were a lot of people who were very arrogant about the place at which physics was located or physics was placed. They thought that everything was addressed, all the theories were sufficient to describe nature, and it was only with a little bit of tweaking that we can come to something which can describe everything as such. So there is this famous quote by Albert Michelson in 1894, and I would like you to look at the last line out here, which says that an eminent physicist remarked that the future truths of physical science are to be looked for in the sixth place of decimals, right? Which basically says that it's only in the precision and accuracy of your application of the theories already present that the rest of the physical sciences would be completely explained. And it is funny because in 1894, when this was said, just a decade after that, and to be more precise, in 1905, we have what is known as the Annus Mirabilis, or the Year of Miracles, by Albert Einstein. And he gave us four papers in that year, and you can see these are the original kind of copies or snapshots of the papers which he published that year, and they related to four different topics. One was that of photoelectric effect, which some of you may be familiar with, the idea being that you have the irradiation of a metallic surface, and given sufficient frequency, you can have the emission of electrons from the surface itself. And that was, of course, not explicable with classical mechanics beyond a point, and we'll come to that shortly. The next paper was that of special relativity, which was a groundbreaking kind of work, of course, and that had led to this questioning of the idea of space and time as absolutes and made it more frame dependent, so to say. The third paper was on Brownian motion, which he worked upon as well, and people don't acknowledge that because the other three are very eminent and famous, right? But there was a very major paper on Brownian motion by Einstein in that year. And lastly, we have the idea of mass-energy equivalence, which is that mass and energy are equivalent to each other, and we have the famous E is equal to mc square equation that is often used in various places in popular science and in various places as such, right? So these were the four different works, and this fundamentally changed the whole landscape of physics itself, right? I mean, these two regimes I was talking about of high speed movement was part of relativity, of course, and the minutest of layers, right? That is what we will be interested in, will be that of quantum mechanics. Right. So just to give you a little bit of context here. So in the 17th and 18th century, we have the idea that there is a wave theory of light. Hooke, Huygens, Euler, they all worked on this. And in 1803, Thomas Young gave us the double slit experiment, Young's double slit experiment. Subsequently, in 1838 and 1897, we have the cathode ray, which was utilized for various kinds of experiments. I happened to have the privilege of looking at or viewing the original cathode ray developed by J.J. Thomson, which is still located at the Cavendish Laboratory in Cambridge. And then finally, we have the Kirchhoff's law of radiative exchange, which talked about how radiation happens from black bodies and in general as well. So this was the state of how physics was at that point. And in the 19th century, when it began, or roughly around the turn of the century, Ludwig Boltzmann gave the idea for the first time in a definite manner that energy, when it is moving in nature, could possibly have something which is discrete, which is in packets of energy, so to say. And subsequently in 1900, it was Max Planck who first gave the statement that the energy of any system is quantized, right? Or the energy of the system is in terms of discrete packets from an oscillator system, right? That was what he mentioned in his statement. And he, of course, focused more on the oscillator model, and then that slowly became the more generalized quantum model of sorts as we went forward. In 1927, you must have all seen this picture, which is that of the Solvay Conference. You can see many luminaries here, from Heisenberg to Schrödinger, Einstein, Planck, Curie, everyone, you name it, and you probably have them here. And so there was a lot of work going on and churning of thought going on in the early part of the 19th century, or rather, sorry, 20th century, and that was what the state of matters were. And then subsequently we had these set of luminaries who came forth, and they completely changed the way we looked at things based on the experiments that were done in the late 19th century and early 20th centuries. And the interesting part is that there were various kinds of contradictory kind of approaches to reality that had to be reconciled with this whole idea of the quantum theory, specifically that of the wave-like nature, which I was talking about previously, and the idea that there is a particle-like nature as well, and what we call as a duality, which is that there are both of these and they coexist for any general system, so to say, but in certain regimes, one is visible and the other is not. And so the people who were most, worthy of being mentioned, according to me, would be those of would be the Niels Bohr, who gave us the Bohr model of the atom. Also gave us various things on complementary variables, which are important set of variables that have certain bounds on them in terms of observations. Then you have Heisenberg, who gave us the famous uncertainty principle, right? And we know about how there is an uncertainty of simultaneous measurement of certain kinds of variables, right? We have often seen about the position momentum kind of case scenario. And of course, he also worked on the matrix formulation of quantum mechanics. Louis de Broglie, he gave us the wave-particle duality that I was talking of a while back. Dirac, of course, gave us the Dirac equation and Fermi-Dirac statistics. A point to note here is that one of our Indian luminaries, Acharya Satyendranath Bose, gave us the idea of the Bose-Einstein condensate and the Bose-Einstein statistics, because of which bosons are named after him. And similarly, because of Fermi and Dirac, fermions are named after Fermi, right? So Dirac was also very instrumental in the Fermi-Dirac statistics formulation. And subsequently, Erwin Schrödinger, of course, not subsequently, actually, it was around this same time. He also gave us the preeminent equation for quantum mechanics, which is that of the Schrödinger equation, which tells us about the dynamical evolution of quantum states or quantum systems, so to say. So that was the context in which we existed till about the 1930s, and this was happening in that period. The 1910s, 1920s were the period when the early formulations and Einstein's photoelectric effect, for instance, and various other developments were happening. And it is of note that Einstein actually got his Nobel Prize for the photoelectric effect and not quite relativity, because relativistic empiricism was still not established conclusively in many parts. And so it was photoelectric effect that was the reason for, the stated kind of scientific research for which he was given the Nobel Prize. And so the important bit was that this whole revolution that was happening and the whole idea of the quantum was basically, as many of you would know, very simply put, the idea that there are certain packets or quantizations of different variables. So you can think of this, interesting illustration where you have a fireman who's going down a pole. So he could, in principle, go down any amount of distance down the pole, and it could be any number in that continuum of heights. Whereas if you were to have a ladder, for instance, then of course you will have a certain stepwise quantized way of doing things. Like in this case, this girl is trying to get this apple by going in certain discrete steps. Similarly, you have energy, momentum, various other properties of a system that were found to have a certain quantization of sorts. Then there was this principle of superposition. And this is interesting because superposition was known to be present in certain kinds of interferometric experimental results. But in the case of the quantum, you have this idea that states themselves, even for certain kinds of, when you're accounting for wave-particle duality as well, have a certain superposition-based approach or a superposition-based reality. And the most famous example, of course, which people often use is that of the Schrödinger cat, right? Where you have this idea that a cat is put into a room with a radioactive source, and there is a certain probability with which the radioactive source can be emitting the radioactive radiation, I mean, so to say, which is harmful for the cat. And there is therefore a certain probability that the cat will, acquire that, or be influenced by that, affected by that, and die, right? And therefore, there is a probability of the cat being alive and dead, right? But however, having said that, if we do not open the room, right, and we were just to describe the state of the cat, then ideally we will have to say that it is in a state of being both dead and alive, right? Which was a very counterintuitive idea. And that is what brought us to these two fundamental points that I have mentioned on the left hand side, which is that of what is reality itself. Is there something which is objective in that reality? Is it dependent on our observations, or is there something pre-existing, right, in terms of the reality and objectivity to it? And the second thing which came forth, which was very important, and I will be touching upon that at greater length shortly, is that of non-locality, which is that you have a certain way in which things are connected across space-time, you could say in generalized form, which is because we also have non-locality in time. There are time crystals where we have found that this idea of correlations existing across time is also seen. So non-locality would basically mean that you can affect the property of something which is very far away, which is spatially very distant, or even in time, for instance, for that matter, in a way where it defies this idea of locality, that things are close to each other and therefore affect each other. We no longer align with that, right? We have a certain principle of non-locality that comes through, and that directly affects, or is the preeminent premise for this idea of decoherence. And I will shortly mention about that. So decoherence is this idea that any system has a certain correlation with its environment. And you all may have heard about this principle of the wave function collapse, right? There is a certain mathematical entity which describes quantum systems, and there is a certain manner in which it collapses. Now, people often say that it is because of consciousness, it's because of various kinds of mind related things. I would like to keep it fairly objective in saying that it is because of certain kinds of correlations between the system itself and the apparatus which is measuring it, that there is a certain quantum to classical movement or transition, so to say, right? So, these are some of the important points that came forth from the quantum side of things, and which I would like to highlight here. And of course, most of you may have known about the postulates of quantum mechanics. I will not go over all of them, but just mention that there are some non-trivial and counterintuitive ideas, like quantum tunneling, for instance, where if you were to have a potential barrier in classical physics, you of course cannot you have to go over it, right? Or you are bounded by it. Whereas in quantum mechanics, if you were to do the math and if you were to do the calculations, there is a certain probability of that particle in a way tunneling through the barrier itself, right? So I would not go over all the postulates because they are kind of mathematical and technical, but I would just highlight that the important bit is that every physical variable that is present in a certain system can be described by what is known as an operator, right? A quantum operator. And there is a certain probability of obtaining a measurement, right? Which is given by the modulus of this eigensystem or eigenvalue, which you get squared, right? And there is the Schrodinger equation, which I had already mentioned, which talks about the dynamical evolution of the system as we go along in time, right? Given certain kinds of potentials that are existing therein. Now, there is obviously the famous hydrogen wave function that you may have seen. There are different kinds of orbitals, and the presence of the electron around the nucleus has a certain probabilistic side to it. There is a distribution, and the patches that you see, which are in white or yellow, have the highest probability of the electrons being found there. And so you see the distribution is very distinct and quite interesting as well. And the idea that was very important, as is seen in the hydrogen atom, is that there is a certain fuzziness, right? There is a certain kind of non-deterministic probabilistic aspect to it, right? So you cannot say for sure where the electron is, but you can give a certain probability of finding it in a certain space, for instance, with a certain probability associated with it, right? So that was the important bit in quantum mechanics in terms of the major rules, so to say, or postulates of quantum mechanics itself. Now, I'll quickly like to go over some of the interpretations of quantum mechanics because this is important in its own way and is of interest to, I'm sure, some of the viewers. This is a certain chart which tells you about the different schools of thought which came forth in the early 20th century. And the major ones were, of course, those of Bohr, Einstein, Bohm, and Everett. Now, Bohr and Einstein believed that the wave functions or the reality as such, the quantum reality, there is no quantum objective reality per se. Like, I mean, at least Bohr was somebody who said that. And he thought that the wave function is just a mathematical tool of describing it. Einstein did believe there is objective reality, but the wave functions themselves are not objective or real per se, right? So he also mentioned that they are probably just probabilistic knowledge of what is happening beneath that layer of description. And finally, there was the idea that the wave functions actually are real, right? There is a reality to it. And for instance, David Bohm talks about pilot waves, right? Pilot waves are these waves that carry the particles as they go along. And so the broad distribution of the schools can be written in terms of psi epistemic. Psi means the wave function. Epistemic means a manner of describing, the descriptory part of it, right? So psi epistemic means that the wave function is only there for describing things. Psi ontic means that the psi, the wave function itself, has an ontological or ontic reality to it, right? So that is why it's called psi ontic and psi epistemic. So this is an important bit on the interpretations of quantum mechanics, and there has been a lot of debate about various theories around it. I mean, I will not be touching upon that all that much, but I thought that this would be of interest to some of the viewers here. So now comes the elephant in the room, right, which is that of quantum entanglement. I'm sure many of the viewers have come across this term in certain popular science lectures, in articles, and various places, right, where it is thrown out, often not in the best possible way, in terms of using it in many contexts. Now, quantum entanglement actually came from the discussion initiated by a trio, which is of Einstein, Podolsky, and Rosen. And in 1935, they published this paper, which was called Can Quantum Mechanical Description of Physical Reality Be Considered Complete? And they were basically, Einstein was not very happy with the way in which there was a probabilistic aspect to quantum theory. He wanted to promote this idea that we actually have a deterministic picture, but it's probabilistic because we don't have certain variables accessible to us, right? We don't have some variables with us, and that is what makes it probabilistic. His way of putting it was known as what is called as the hidden variable theory, right? Or the and this has been a part of the debate around what is the quantum theory as such fundamentally. And around the same time, Schrödinger also looked at the spooky nature of quantum physics, and he gave the term Wahrschränkung, which is basically the first term for entanglement in 1935. And the idea behind entanglement is that you have a certain global state, right? A state of a large system, which cannot be described in terms of the constituents per se, right? So there is this idea of reductionism, which we often talk about, which is that anything can be described in terms of the properties and dynamics of its constituents. That was kind of turned around, and this was negated, so to say. And because of this, there was a lot of debate about what is the correct way to look at this. Now, Einstein said that the hidden variable theory should be the one, right? And for a good 30 years, so 1935 is when this paper was published, May 15, 1935. And in 1964 is when John Bell, the British physicist, came out with the Bell's inequality and the violation of Bell's inequality, and then showed that the hidden variable theory is not correct, right? So the idea that there is a hidden variable or some hidden variables and we don't have access to it, and that is why this is all probabilistic, that was kind of put to the side, right? So Einstein, well, at his best, laughing at certain things, till the very end, did not like the probabilistic approach, but it is what it is, given the kind of experimentation and theorization that happened in the subsequent decades, so to say. So the idea behind this Einsteinian picture was that there are certain ways in which properties of particles can be correlated, right, in a manner which defies the conventional classical understanding or the deterministic understanding. So the way in which they went about with it was looking at the decay of a single uncharged scalar particle, right, into this positive electron pair, right, and because there is no orbital angular momentum for this pair, we can have the conservation of the orbital angular momentums, and we can have an understanding given the measurement of one, let's say the electron, right, about the property of the other in a certain manner of speaking, right? And so there is a certain way in which there is a non-local aspect to it, right? You are separating them spatially, but there is still a certain linkage of sorts, right? A certain manner of tracking that can happen in a non-local manner, right? So this was an early manner of showing this experiment or this thought. Then thereafter, as I said, John Bell in 1964 said that, okay, let us assume that the hidden variable theory is the theory of everything, right? Or rather, sorry, the theory of quantum mechanics, not the theory of everything. And let us test that, right? Let us test that idea or that premise. And he assumed three important assumptions, which is that of reality, locality, and free will. Right? What does this mean? Reality means that there is a certain objective reality to the various things happening in the constituent systems, regardless of how or in which way we are doing the experiments or observing it, so to say. Right? Locality, of course, means that there is a local reality to it. There is something which is, for lack of a better word, spatially connected or in some ways causally connected to each other, right? In the conventional classical physics terms. And free will means that you have the free will of any person of measuring the particles in whichever way they want, right? So he had formulated these inequalities based on these three assumptions, and then he found that actually the hidden variable theory does not quite do justice in terms of what is the inequality itself. I mean, the inequality is kind of violated, right? And that is not something the hidden variable theory, because of which the hidden variable theory cannot be taken as a quantum theory as such. And so that was what was found, and therefore there is this famous inequality called the CHSH inequality. And you can see this graph here. I mean, I'll not go into too much of the technical aspect right now, but the idea was that there was a graphical or rather a numerical result which showed that the quantum side does not quite match with the hidden variable assumption and the way we were looking at things. And therefore, there is the Copenhagen interpretation, the probabilistic interpretation of quantum mechanics, which was taken as a preeminent approach or the interpretation that had to be carried forward, right? So this was an important part of all the build up towards this quantum technology being developed, and quantum entanglement itself, right, can be seen in many different kinds of systems. So it can be seen in, for instance, what were known as the Bell states. So you just heard about the Bell inequalities. There were certain kinds of systems which had the optimal correlations between them, which were called the Bell states, right? The Bell states were basically maximally entangled states, right, which you may have come across, where there is a one-to-one correspondence between the state of one subsystem and the state of the other. And this kind of correlation can be found in higher dimensional states also, right? For instance, what are known as GHZ states, which are basically, as you can see on the top right-hand side corner, is nothing but the tensorial product of different zeros and ones in a certain combination that are in superposition, so to say, right? And so this was seen in different kinds of systems, and this could be used in a manner for the resources in information processing, and that is what basically was the movement towards quantum computing. And it was only at the beginning of the 1990s that the most general theoretical results around these were found. And these states could also be part of, let's say, a lattice, right, or a certain structure, right, which was distributed in space, right? And you could utilize the resources in that using what is known as measurement-based quantum computing formalism, right? And I'll touch upon that briefly. So there were many ways in which quantum entanglement could be used for both circuit-based as well as measurement-based quantum computing formalisms, so to say, right? So there are these things called cluster states, which you can develop using the correlations between different nodes, which are basically the quantum states themselves. And so, in the early, or rather, the second part of the 20th century, the experiments around this started to happen. And you may have come across the name of Alan Aspect, who got the Nobel Prize recently. He was the one who formulated one of the first convincing experimental tests for the Bell inequalities. and the basic schematic is given as here with, right? You have a certain source from which two different particles emerge. There is a certain beam splitter, and there is what is known as a coincidence detector, which looks at the coincidences in the different tracks or channels where the particle comes through or not, right? So you have a certain inequality. I just showed you an inequality, which is called the CHSH inequality, and that uses this information from the various tracks and channels in the Allen aspect model, or the formulation, so to say. And thereafter, there were various other experiments as well, right, which were done around this period. I've given some references. If any of you are interested, I could forward this information to you. Especially Gissin and Brendel. They were very, very important people, as well as Zeilinger, who was, of course, an important figure as well. And most importantly, Mandel and Wu, who also worked on many different experiments when it came to the quantum formalism, and looking at the local hidden variable models, which were of importance at that point. So now you may ask whether entanglement is actually generated or not, right? Is there a generation, or is this just a theoretical idea? It is very much an experimental reality of sorts. You have this idea of the this non-linear crystal, right, which is a crystal that has certain kinds of non-linearities in its constitution, because of which any light that is made to pass through it gives rise to certain kinds of correlated light on the other side, right? So you can have, for instance, two beams coming out with some correlated properties or entanglement inherent in them, depending on what kind of crystal you have, right? So you have this seen in the laboratory. There's a science paper in 2019 which shows you basically this very interesting donut-like figure. So if you look at any point in that shape, right, the donut-like shape, the point that is diametrically opposite to that would roughly have the other beam which is correlated with it, right? So, or which is entangled with it, right? So you can see this kind of distribution that comes through in multiple runs with a certain nonlinear crystal aspect of it, right? So that is one of the ways in which we develop or generate entanglement. There are other ways also, like excitons, and there are many other ways also that have been developed recently. But this is one of the main, the early ones, right, which had been extensively utilized in different laboratories. Okay. Now, when we talk about entanglement itself, right, there are different kinds of postulates of entanglement, right? One is that there is this idea that if you were to have a local operation or classical communication, entanglement cannot increase because of that, right? And that is important because entanglement is a non-local correlation, right? So locality or operations which are done locally, right, and the classicality of of communication, if any, should not basically influence the entanglement itself. And of course, because it's a correlated state, any system which is separable. What does separable mean? That the whole can be made into its parts, in a sum of its parts, right? And you can separate out the constituents, right? Or at least the description of the constituents. That is not possible. Entanglement vanishes on certain separable states, on all separable states for that matter, right? So now the question is, how do you quantify entanglement, right? There are certain ways in which we quantify entanglement. And I wouldn't go too much into the depths of that because that will take up an entire session in itself. But there are ways in which you can, for instance, define distance measures, right, which are how distant a certain reference state is from, let's say, a separable or an entangled state. And there are different kinds of protocols, like the PPT distillation protocol and relative entropy of entanglement, and so on and so forth. There is also the other state, or the other set of characterizations called as convex roof constructions, right, which can be obtained by having a certain convex roof, as it is called, a mathematical tool of sorts, which is on certain kinds of mixed states, so to say, right? So concurrence and various other measures, for instance, are in this manner. And you can have various measures. So you can have things like logarithmic negativity. There is the Rains bound, which is often used as well, and the maximal teleportation fidelity, right? How well this application called teleportation, and I'll touch upon what teleportation means, can be done with, let's say, a certain state, right, or with a certain kind of resource that is available. And then there, in 2007, we had something which was a generic method to generate a new kind of entanglement measure called conditional entanglement. entanglement, and that can be constructed using previously defined entanglement measures as such, right? So that's the most generalized kind of form of characterization for entanglement possible in a certain manner of speaking. There are other works also that have come from that time, but this is a major work that was done. Now, when we are talking about entanglement and the idea of correlations, one of the things where it is utilized and you have often seen in many kinds of talks and lectures and presentations, I'm sure, is that of teleportation, right? Now, the reason I've given the picture on the left hand side is because the teleportation that you see on Star Trek, right? It's not quite that same teleportation, right? Teleportation in the quantum sense is not that you are zooming Captain Spock from a certain place and zooming them into some other place, right? It is more that you take the information inherent in Captain Spock or a quantum state, right? And you transport that using a quantum channel and reconstruct the state in a certain different location, right? With the inherent resources available, right? So I have given a very simple schematic on the right hand side bottom, which is that of this teleportation scheme. The idea is that you have an EPR source. EPR source is basically, you can think of it as a Bell state, right? Which has maximal entanglement. So there is one beam that is coming from the EPR source towards Alice, right? Alice out here, and one which is going to Bob. There is another person called Bob, and there is an unknown state that is also being sent to Alice, right? Now, the first qubit or the first element that is being sent to Alice from the EPR source and the unknown quantum state that was available, we do a joint Bell state measurement on that, right? And based on the result of that state, right, Alice sends a classical communication to Bob, right, who has the other unit from the EPR source available to him. And based on this measurement done in the Bell state measurement, Bob undertakes a unitary transformation, right, and gets back the state that was unknown and which had been initially passed to Alice on his terminal. Right? So you see what's happening here is that the state itself no longer remains with that first qubit. It is rather reconstructed and available now with Bob, but in a different physical qubit itself. Right? The qubit itself is a different physical qubit, but it has the same logical state, right? In a manner of speaking, right? So that is a very important point. It's not quite the teleportation in the physical sense, so to say, right? So entanglement theory actually has these applications like cryptography and superdense coding, teleportation. So in the early years, 1991, 92, 93, right, there were a lot of papers by Bennett, Eckert, there was Perez papers, Yossa is very famous as well, Wouters, right? These were all people who had been working on the different applications and how entanglement can be generated and utilized for different purposes, right? And so you have again given us few references if any of you are interested, where the demonstration of these effects and how it can be utilized was shown in experiments as well, right? In 97, for instance, Zeilinger again worked on this. And then you have Branca, Martini, Hardy, Boschi, and Popescu. That's a very well-known paper in 1998, which was published in Physical Review Letters as well, right? So that is a general introduction of the initial parts of how quantum entanglement started being used in information processing tasks in different contexts like cryptography, teleportation, and so on. Now, entanglement itself can be, as I have said here in these broad points, manipulated, right, in various ways, broadcast, and also controlled and distributed, right? Now, the thing is, entanglement can also happen, and this is very important because I'll be touching upon this later in the presentation, in different degrees of freedom, right? So you can have, for instance, entanglement in the orbital angular momentum degree of freedom of a certain photonic system, as well as in, let's say, the polarization degree of freedom as well, or the path degree of freedom of that light. What do I mean by that? That if you were to have different kinds of variables or properties, right, you could have entanglement across these as well, right? So I'm saying that correlations don't exist only between particles, but could also exist between the degrees of freedom of one single particle as well, right? And that is, as you may appreciate, very useful because what we are saying is that for the same physical substrate or same physical qubit, you can have multiple logical states and resources available to you, right? And that is of importance for things like hyperentanglement and hybrid entanglement, right? I'll come to that shortly. And so you can do these various kinds of operations with entanglement, and entanglement can be brought into information processing tasks in this manner, right? So that's of importance, so to say. And again, I have given resources. If any of you are interested, we can have further discussions on that. Let me just see if there is anything worth highlighting most. I think Chirac and Zoller's paper in 2004 on the control and distribution of entanglement is an important one, as well as Harosh. Sergei Harosh is somebody who has got the Nobel Prize as well, and Raymond and Brune in 2001, review of modern physics paper, which was published in 2001. That is also very, very interesting and important. Okay. Now, quantum computing itself, right? I had mentioned about Eckert and so on, various others as well. The history, of course, is slightly more involved, slightly longer. So Solvay conference, of course, I showed you in one of the previous slides, but it was in the latter part of the 20th century, particularly around the 1970s and 80s, that this idea came forth that we have the quantum domain. Right now, what do we do with that? Right? I mean, there is a lot they already did with that. Right? You had the transistors and various other phenomena that you kind of undertook. There was what we known as the quantum revolution one, right? 1.0, right? But there was more that could be done, right? So Holevo, you see the first picture there, Holevo bound. Holevo gave us this bound on the amount of information that can be carried by the classical and the quantum and its classical counterparts when we're talking about a certain physical platform, right, or a certain physical carrier of the information, so to say, right? Then in 1980, Benioff, right, he gave us the first quantum Turing machine, right, the quantum Turing machine, which was an interesting development on the classical Turing machine, which had been around for a while, right? And in 1981, Richard Feynman, he gave us this idea that if you need to simulate a quantum system, right, or you need to do certain kinds of calculations based on quantum systems, why don't we utilize the quantum systems themselves to form a substrate for computation, right? So there's a famous speech by Richard Feynman in 1981 where he talks about this, and you all can go and have a look. It's an interesting speech where he tries to have a very interdisciplinary approach, as you would call it in modern parlance, right? It's a buzzword now, interdisciplinary. Now, the thing is, he was one of the people in physics who did a lot of these interdisciplinary works across the board, and this was one of them. And in 1982, you had this idea or the theorem called the no cloning theorem that was put forth. The idea is, as some of you or many of you may know, that quantum state cannot be cloned perfectly, right? It cannot be replicated, so to say. And there is a certain no-go theorem that is present in terms of the no cloning theorem that we have. And in 1985, David Deutsch, whom I have had the privilege of talking to as well, in Oxford University, had the first universal quantum computer, which was developed by him, right? And he put forth the various aspects of that. And on the top, you can see the small chip. This was something that I myself was involved with in Cambridge University. And this is basically to look at how electrons can be made to move through certain silicon heterostructures and made to have quantum states and correlations developed in them. Right? So I will not go too much into detail on that, but this was an actual kind of implementation or realization of how quantum mechanics and quantum computing can be done in certain kinds of condensed matter systems. Right? Now, I have already mentioned about superposition and this idea of entanglement, so I'll not go further into this infographic that I've shared. The idea being that, and one important point here is that entanglement is not the only non-local correlation, right? There is a broader class of correlations called quantum discord, right? And there are even further ones as well. And entanglement happens to be a certain subset of that, but often utilized most in many different kinds of applications, right? So that's of importance, and I just want to highlight that. And when we are talking about quantum computing, and this is a bit of a overview of sorts, you could say, this slide. It has been utilized in different applications today, right? And it's actively being utilized in others as well, like chemistry, for instance, right? Optimization, different kinds of optimization schemes, material science to develop or rather find different kinds of novel materials, also in machine learning and cryptography as well. And of course, communication channels, right? How to do advanced next generation communication is also very, very important. And the quantum communication communication protocols have been slowly developed to do that, right? And when we are talking about quantum computing, there are different kinds of physical platforms that can possibly bring about this, this formalism, and they include superconducting systems, right, where you have things like transmon qubits, and there are different kinds of companies and other institutions that are working on that, including Google and IBM. Then you have trapped ions, right, where you have certain kinds of charged atoms confined in certain spaces, and then you can manipulate them using different kinds of electrons or other stimulants, so to say, or other ways of perturbing them. And they are also utilized in many ways. They're highly stable. That is a very important point. The trapped ions are highly stable, and they have also high gate fidelities. When you are doing operations in computations, you often have gates, right? You may know about classical gates and quantum gates. So that is also something which is useful in the trapped ions. Then you have silicon quantum dots, which I have worked on in the recent past, and they have Intel is working on that. They are also fairly stable, but the only problem is that only a few of them can be entangled at a certain point in time, right? So these artificial atoms have limited kind of entanglement, prospects, so to say. Then you have the topological qubits, where Microsoft is working on this. The idea behind this is that you have different quasi particles in condensed matter systems, and they have a very low error, essentially, in them, error margin, so to say, and yet they haven't been proven per se beyond a point, as in they haven't been realized in a major way or in a conclusive manner in various systems that have been done experimentally. And then you also have something called the diamond vacancies, NV centers and diamond vacancies, where you have these vacancies created in certain kinds of condensed matter systems, right? And they can operate. One good thing about this is that they can operate at room temperature as well, right? So there is a certain idea that if you have a quantum computer, it has to work in room temperature conditions, of course, right? And one thing I would like to highlight here is that each of these platforms have different pros and cons, right? There is this idea that if you were to have a quantum bit, right, a small unit of information, what is its longevity? How long can it exist for, right? And that is a very important part. But also what is important is what is the logic success rate, right? If you have a certain operation, a circuitry, what is the success rate that you will have for that logical operation, as well as how many number of qubits can you actually entangle, right? So now we are working with very, very large systems. IBM has about 43 to, I mean, it's going towards 70s and 80 qubits in one system, and even beyond. It has very ambitious plans, as I'll highlight shortly, right? So we are going in that way. So we cannot have some system where we cannot do that kind of entanglement, so to say, right? Or there is no, specific unit in which we can do that, or in a specific way we can do that in a proper manner, right? So that is of importance, and I just wanted to highlight that. So when we talk about teleportation, this slide actually I wanted to put forth because the schematic may be very straightforward, right? And this paper, this graph rather, or setup, has been around for a long period of time, right? It has been around since I think the 1980s or 90s probably, sorry, and early 2000s. Also, there were some variants and so on. Now the thing is, I showed you the schematic for teleportation, right? This is the manner the entire thing actually happens, right? So I'll tell you why this is very non-trivial and not that easy to undertake, right? I mean, in India, we have very limited labs which are working on teleportation in the experimental sense, right? So you have the EPR production, the pair, the maximally entangled state produced in this box that you see on the right-hand side, right? The Alice measurement box is on the left-hand side, and Bob remains in that small little box in the bottom right-hand side corner. Now, the way they're doing this here is using the SPDC process. I just showed you that you can use nonlinear crystals to undertake entanglement generation. Now, SPDC itself has a very high degree of inefficiency, right? Because for every million pump photons, right, 10 to the power 6 pump photons, you will probably have about 2 to 4 pairs of entangled states that come forth, right? So firstly, that is a big problem, right? Thereafter, you have different kinds of elements, right? Linear and nonlinear elements, which are again have their associated problems of alignment. There are various different causes of errors that can come through, right? And because we want a very fine-tuned resource and manner of doing this, it is highly non-trivial, right? So, but however, we are making progress in the sense that we now have on-chip, ways of realizing this. And one of my friends, Dr. Raktim Haldar from the I think in the École Polytechnique schools and in France, have shown how the laser sources and various integrative elements can be put on a laser on a chip, right? And various things can be done with that, right? So it is of importance and note to understand that logically there are a lot of things we can do with quantum mechanics, but in terms of experimentation, there are a number of constraints. And one of the major constraints actually also is that the quantum systems have a very delicate quantum nest in them, right? In the sense that because they have the tendency to entangle with their environment, any state can easily lose their quantum nest, so to say, and become classical in nature, right? The decoherence, as we were talking about, is something that is of importance and something to be protected against, right? So there are these few points I wanted to highlight before we move forward in terms of this beautiful quest to understand quantum technology, right? So I have already looked into this. Now, the thing is, here we have some of these ways in which quantum information, or entanglement rather, can be utilized beyond and besides the information processing itself, right? So, of course, one is that the communication complexity, right? If you were to take it as a theoretical problem, it has been seen by Bruckner, Berman, and various others that the communication complexity for a protocol assisted by states which violate the Bell inequality is more efficient than that of the classical ones, right? There is also this very interesting problem where if you were to have two people and they had an entangled particle pair, right? Can they find their orientation in space, right? Is there a manner in which we can undertake this correlation? Can it help in terms of placements and so on and so forth, right? Then you also have frequency standards and clock synchronization that can be developed and improved further, right? With different kinds of transitions in cold ions, right? And that in that also people have been looking at whether entanglement and various correlations can help in that respect, right? So entanglement in general, I've mentioned in the bottom side of the bottom half of the slide, or rather the last line of the slide, is seen in various different kinds of systems, right? You have superconductivity, you have spin systems, of course, even the question of emergence of classicality, right? That is of importance. So there are a number of works that have been done and platforms thereof which can be utilized for this as such. So when we are talking about quantum computation, right, there are primarily three different formalisms or frameworks which are of importance. One is that of the gate-based circuitry or the gate-based quantum computing, which is basically just like in the classical case, you have different kinds of transformations or gates, right, which can be applied on certain channels and states. On the right-hand side, you can see the IBM quantum experience, right? Some of you may have utilized it. The idea is that you have, let's say, a circuit composer, right, with standard quantum gates, and you can utilize them on a reference input register and find out the measurement patterns and look at the visualization thereof as well. The second manner of doing quantum computation is a measurement-based quantum computing, which I briefly touched upon. The idea there is that you have a one shot or one time measurement of the different states of the system. And based on the measurements, you do subsequent transformations and operations, and the computing goes forward in that manner, right? So it's based on the measurements. And as you may appreciate in quantum physics, because there is a problem of wave function collapse, once the measurement is done, right, that resource no longer exists as a viable resource, right, unless you have some other way to generate entanglement, in that system, right, immediately or in some time. That basically is removed from the system, so to say, right? So there are things like, for instance, lattice surgery that is done in this formalism, where you basically try to remove certain kinds of systems with the standardized, controlled measurement, system or protocol, right? So, and the third one is basically when you have functional quantum computation, where instead of qubits, you basically have operations or functions as the fundamental building blocks, right? So, in some form or the other, I have touched upon all of them in my career and my time undertaking research in this area. So, I'll briefly like to mention about some of them. Okay, so as Ashiji was mentioning, I have had this trajectory till now, and this has been since 2012. So in most of these parts, I have their various attainments or parts that I've covered in the quantum computing realm. So I'll touch upon some of them, and in the process also try to highlight what is of importance there. So in 2012 to 14, the idea that I was looking at was at multipartite, generally entangled states, specifically a 7-qubit state, right, which was developed around that time, and how to utilize that. Firstly, to characterize that, right, and then to utilize that for teleportation of a single qubit state, a double qubit state, and a arbitrary 3-qubit state as well, right? That was part of the problem. And as you can see, that the decomposition itself is highly non-trivial, right, and has very specialized unitary operations that are associated with each of these outcomes, so to say, right? And then we also looked at quantum secret sharing. There were some proposals that were proposed because of this, right? Now, the point here I would like to highlight is that you have different systems where entanglement can be generated for sure, right? But the manner of manipulating it and the manner of utilizing it is very, very fine-tuned, is very, very specific to different protocols. And the point here is that there is a trade-off when we are trying to develop entanglement further, given a certain resource, because there is something known as entanglement monogamy. What does that mean? Entanglement monogamy means that if you were to have a couple of qubits, let's say, and they are entangled with each other, introducing a third qubit and trying to entangle that with the first two, right, will have a trade-off or an effect on the entanglement of the first two themselves, right? So there is a manner in which it has to be fine-tuned, the maximally entangled states and the partially entangled states, right? And how you introduce, where do you introduce various bits? How do you utilize the measurement operations? And so it's a non-trivial but an interesting process, right, to see how these different kinds of formalisms and mechanisms can be undertaken, right? And then we also looked at this idea of the measurement-based quantum computing, right? So I just told you in the last to last slide about how you can have a stationary qubit, right? And you can measure them. And that measurement process, right, going in a sequence, right, leads to a certain kind of protocol that can be defined on that substrate, right? So you usually have, for instance, a plus or minus state, which is basically a 0 plus minus 1 by root 2 state. I'll not go into the technical aspects too much here, but there are certain kinds of qubit states which are used for initialization, and you have something known as a CZ gate, right, which is utilized for developing the correlations between the different kinds of nodes, right? So you develop a certain lattice almost, or a cluster state as it is called often, and then you utilize that for different kinds of operations, right? So you have operations like fusion operation, which is nothing but creating a larger number of cluster states from a given set of cluster states, for instance. And you can have three-dimensional cluster states. You can have things like lattice surgery that I had mentioned about, right, where you can remove a certain part of the lattice as well, given certain kinds of measurements you do on them, right? So that is of importance here. And a cluster state itself is what is technically, the technical definition would be a highly entangled quantum stabilizer graph state, right? Basically, the idea here is there is a high level of entanglement, right? However, please note that I have not mentioned that it is maximally entangled, right? Usually, because I'll show you the mathematical definition as well, it's not quite maximally entangled. It has a certain partial aspect to it. And quantum stabilizer means that there are certain kinds of operations which can give us an understanding of what are known as error syndromes, right? Or what kind of errors may have crept in. And graph states, of course, as the name suggests, is something that is defined on a graph, right? It could be a two-dimensional, three-dimensional graph. And therefore, we can have a certain formulation of this system, which can be utilized for different kinds of processes, right? Now, because it is a certain probabilistic approach, right, it is much more easy to kind of undertake coherent gates on measurement-based quantum computing, right? So what I mean by that is that because you can have, let's say, SPDC that I was talking about, right? They have a certain probabilistic aspect, right? There's a certain efficiency factor to it, right? But because here we are talking about, often we're talking about ensembles or multiple runs and a probabilistic side to things, right? The reconciliation of these two aspects can be easier with the measurement-based systems, right? So, and there is an adaptive manner in which we work to undertake the measurements one after the other, right? And that's how we do the quantum computing with measurement-based quantum systems. So mathematically, the manner in which Rosendorff was the first one of the first people to describe this, or rather the person to actually define it. He said that a cluster state, right, is nothing but the set of states which satisfy the eigenvalue equations given here on the left hand side, and the eigenvalue operations have these operators which have a tensor product of the x and z operators, sigma operators, in a very specific manner, right? So if you were to take, let's say, sigma x, right? Sigma x is a Pauli matrix, as it is called, or an operator, right, which is used in spin systems, for instance, right? Then you would have the neighboring ones to be having the sigma z, right? So there's a very distinct kind of construction of the super operator, so to say, right, of which the cluster state should be an eigen vector, right? That is the whole idea. And based on which kind of cluster state it is, you will have the plus or minus kind of characterization of the eigenvalue, right? So the way in which we undertake that is to use what are known as plus or minus states, right? And we have what are known as these C phase operators, which I said CZ gates that I was mentioning about, which can be described in the manner shown at the bottom of the slide. You see that SAB, right? That is where you have, if the state is in a if the first qubit is in the state 0, right, then there is nothing that happens. But if the first qubit is in the state 1, then there is a sigma z operation that is undertaken, right? A C naught operation, which some of you may have seen, is a control naught operation, where instead of the CZ, it is CX, sigma x, right? Sigma x, basically what it does, it flips the second qubit if the first qubit is in the 1 state, right? So Boykin et al., there are these people who, Oscar and Boykin, who showed that using measurement-based systems, you can have universal quantum computing, right? What does it mean to have universal quantum computing? It means that you can basically undertake any general arbitrary operation, right? Using a set of basic operations like Hadamard, there's a gate called Hadamard gate, C naught gate, and so on. And you can undertake that in a certain specific system, so to say, right? So that is what a universality of quantum computation means. And there are some other rules also. Di Vincenzo had given 5 different criteria for how this can be undertaken in a systematic manner, right? So this can be done in the measurement-based system, is what is of importance from this slide. But the problem with the problem with measurement-based systems is that because they are one-time measurement systems, the way of undertaking gates like C naught gate, right, is highly non-trivial, right? So you have, for instance, 15 different qubits, stationary qubits, right? And you have a sequence of operations that have to be done in a certain manner, and then the unitary transformation on the resultant qubits have to be undertaken based on what the measurements have given us, right? So there is a highly kind of extended realization approach, right, over many different physical qubits, which are required for things like the C naught operation, right? Whereas in the gate-based one, you just place the gate in between the channels, right? I mean, that's a very gross simplification of things, of course, right? But at least there isn't multiple qubits, physical qubits being utilized, so to say, right, in that operation as such, which is the case here. Having said that, the measurement-based system is more robust to noise as well, right? So noise, when it comes in, that is something which is protected against by the measurement-based system. Similarly, you have the arbitrary rotation gate, which also requires 5 qubits, right? It is not just one arbitrary gate that can be put in. There are a number of different physical qubits that have to be utilized for undertaking that arbitrary rotation gate as such, right? So I've just highlighted what are the different operations and the corrective unitary transformations that are required for that. Now, in Cambridge, we were looking at, I had shown you that chip, right? The idea that the power of swap operation is something which is, as you can see here, I've written it in the heading. The power of swap operation is entangling operator, right? It's an entangling operator if the power of the swap is a distinct power of that swap, right? So if you have, let's say, the square of the swap operation, then that is seen to have some degree of entanglement it generates, but it could have any arbitrary power as well. The swap operation, as the name suggests, is basically to swap the different kinds of qubits, right? So the 2 qubits, for instance, can be swapped. Now you can have a power of swap, which is a partially realized swap, you could say, but in a mathematical format, there is a certain structure, right, matrix structure that you can develop with that. So during my time at Cambridge, we were trying to look at how gate-based and cluster state-based or measurement state-based quantum information processing can be undertaken using the power of swap as an entangling operation, right? And that is of importance because many different kinds of systems have for instance, Heisenberg exchange interaction. The swap operation can be realized in different kinds of condensed matter as well as optical systems, and therefore this can be a very good resource for quantum computing using the swap operation, so to say, right? So during that time, I had also looked at how to find the realization of some kinds of generation protocols, right? What do I mean by that? If I were to have an n qubit state, right, could I possibly have entangled states coming from that, right? Do I have some kinds of correlations, specific correlations that I can develop using the resources available to me, right? So we had developed this null space approach to find that out for any generic n qubit state, right, given the power of swap operation as our entangling operator, right? And that is of importance in this particular bit. And then we realized some algorithms, right? There are some Deutsch-Josa algorithm, which is a very famous algorithm, which looks at how the mapping, right, of output values is done to two different categories of functions, right? One is called the constant functions, and the other is the balanced function, right? So you can undertake a certain mapping, right, using Deutsch-Josa algorithm. And in this case, it was done in a slightly different manner than the conventional way it is usually done, right? So that is of importance here. I've already gone through the characterization bit a little bit, but in our study, we had also tried to formulate novel ways of doing that, including using a partition permutation method, which had been utilized for different subsystems of the quantum state. And there are also things like permutation operators and separability of different, what is called as k-separability. What does k-separability mean? That if you were to have a system and you partition them into different units, right, can you have partial separability or partial entanglement in certain ways, right? And it is very interesting to look at those kinds of separability criteria and how permutations can be used. And also there is a famous positive partial transpose, right, which basically says that if you were to have a density operator of a quantum state, the eigenvalues of the transpose, right, of that density operator, if they are non-negative, then we can say that the state is separable, right? So there is a certain criteria called the PPT criteria, which we can utilize for characterization of entanglement. Okay. And then finally, we also looked at how to see dynamical cluster states, right? And whether they can be, whether we always used cluster state or measurement state quantum computing for stationary qubits. But if we were to introduce a certain movement aspect to it, does that change or so does that improve the manner in which computation can be done, right? So we did see that there are some ways in which, optimization can be done such that the idea of gate-based and measurement-based both can be concurrently utilized for this purpose, right, in a manner of speaking. And there are some generalized cluster states which we had looked at as well. And the idea here is that you have the elements defined, but in a higher dimensional space. Also, you can have a higher dimensional space, which means that qubits usually have the two states, 0 and 1, right? But if you have to have, let's say, a higher dimensional space, you would have 0, 1, 2, 3, for instance, right? And therefore, the operators also would be accordingly calibrated or changed to account for that higher dimensional space, right? So that is of importance. And all the operators, control naught, for instance, becomes a C mult, right? A control multiplication operator, and so on. Right? So this is of interest for generalized measurement-based systems, right, or cluster states. Okay, and now then comes the point where I started to look at how the idea of entanglement, right, can be utilized for different degrees of freedom. I had mentioned earlier in the slides that there are different degrees of freedom that can be utilized as well. So before going into that, the cluster state, just extending the discussion of the cluster states can also be defined or described in photonic systems, right, optical systems. And you'll be amazed to know that in 2019, 30,000 entangled modes, right, were developed or generated in a cylindrical lattice, right, with this very specific architecture, right, which was done by Larsen et al. And published in Science, right? And this is basically gives you an understanding of that. I will briefly touch upon what is happening here, right? So the idea here is that you have two rails. It's called a dual rail architecture, right? There are two channels essentially. and the correlations are taking place because of the beam splitter operation, right? The BS1, BS2, and BS3. And what is happening is, after every generation of entanglement or correlation, we are partially um, uh, moving the one of the rails, right, a little ahead or a little behind than the other one, right? So this, you see this tau, right? This is basically a time delay, right? 1 unit of time delay, and then there is another entanglement, right? And then there is an n times of tau, which is another higher time delay, and then a BS3, right? So what is happening here is, if you see the diagram at the bottom, right, basically the entanglement is generated, a correlation is generated between the qubits here initially, right? So you can think of them as being a line being drawn between them, right? Now when the delay is put, right, the line becomes tilted, right, because one is moving faster than the other now, right? And then when the finally the other one is put in, then there is another kind of shifting of sorts, and finally what we get is this kind of a very interesting cluster state, right, which is generated, and that can be further simplified to a simple graph state, which we were seeing earlier in the presentation, right? So this is a manner in which the scheme for 2D cluster state generation was done using optical systems and these temporal modes, so to say, right? APR pairs and temporal modes. Okay. And so the way in which we undertake entanglement generation, I've already shown you here. There is also this idea of quantum key distribution. Some of you may have come across this idea, right? Where an eavesdropper, right, if they were to try to understand what is the communication happening between Alice and Bob, let's say, right, to the sender and the receiver, there are certain ways in which that can be tracked, right? Because we know that in quantum systems, measurement, right, or any kind of interference, right, has an impact on the state of the system, right, and therefore there are ways in which reference mapping or reference checks can be put in place in such architectures and systems as such, right? So that is of importance. I won't go too much into that in this presentation, but just to touch upon what is quantum key distribution. So now coming back to the point of hyper entanglement or hybrid entanglement, the idea here is that you can have correlations between different degrees of freedom, right? So if you have, let's say, in a photonic system, you have frequency, the spatial mode, the polarization, and so on and so forth, you can have entanglement across and in between these degrees of freedom, right? And the way to characterize it is using, again, different kinds of characterizations. There's this thing called the hyper entanglement witness, right, which is defined in a certain manner. And you can think of it as just entanglement, but utilizing more logical states per unit physical resources, right? What do I mean by that? You have a limited number of physical resources, but you extend the multiplicity of logical states or logical resources premised on that, right? Or based on that given physical resource, so to say, right? So that is of importance here. And this has already been looked at in different kinds of systems. So you have, for instance, so let me before that. So hyper entanglement means that you have entanglement in different degrees of freedom themselves, right? What do I mean by that? So if I were to take polarization, right? If there is a correlation within polarization, right? And there is a correlation in the orbital angular momentum, and there is a correlation in the emission time, right, separate to each other, right, then that can be talked of in terms of hyper entanglement, right? Now there is debate about which is hyper and which is hybrid, but that is the convention I'm taking for the purposes of this presentation right now. And hybrid entanglement would mean that you have entanglement across the degrees of freedom, which means that if you were to have, let's say, polarization, right, and orbital angular momentum, there is a one-to-one correspondence to the states in the two degrees of freedom, right? So that can also be developed in certain kinds of systems. And the diagram you see here is from the city of Vienna, right? They had tried to do a certain hyper entanglement based kind of approach, right? And tried to see if free space links can be done using high dimensional entanglement, right, across different sectors of the city, right? So you can see that there are some places where the hyperentanglement photon is generated. There is something known as a polarization energy time analyzer, right, which is part of this sector on the left-hand side bottom. And then you have the receiver module, which is in a very far away, distant location in the city of Vienna, right? And you can see the buildings, right? These are all buildings. You can see small buildings around. So that gives you a certain idea of the map scale, right, as well, and the orientation. Okay. And then on the right hand side, you can see the hyper entanglement generated in certain photonic systems, right? So here you will have these H, you see on the right hand side top corner, H prime, VV prime, and so on and so forth, and bottom left hand side corner, again H prime, VV prime. These are the ones which have different kinds of correlations inherent in them, right? And this is done using elements like beam splitters, polarization beam splitters, and the various kinds of half wave plates, various kinds of elements that are utilized, and one can generate entanglement. Here, the hyperentanglement is between the polarization and the spatial modes, right? The spatial modes are the channels they're going through, and the and then the polarization of that particular state. So this was something that I was looking at a couple of years back, to how to have an arbitrary hyperconditional gate, right? So if you have a hyperentangled gate and you have 2 degrees of freedom, so I told you about C naught operations, right? C naught and C phase operations, which are basically that given the state of 1 qubit, a certain operation is done on the second qubit, right? Similarly, if you were to do it across the degrees of freedom, is there a simple way to do that, right? And it turns out that there is, right? So you can have a cascaded kind of system where there is a manipulation of one channel conditionally, right, based on the state of the first degree of freedom, right, and the other channel is left alone, right? So you have what can be described as a one-to-one correspondence, which is generated between one state of the first degree of freedom and a specific unique state of the second degree of freedom, and so on and so forth, right? So that is what was developed during this study that we had undertaken, and we had shown it for a specific polarization controlled hyper C phase scheme in the orbital angular momentum degree of freedom, right? So that is of importance out here. And thereafter, I had touched upon this idea of whether entanglement or hyperentanglement can also be utilized for networks, right? You may have all seen classical networks, right? So there are many different networks where what the problem is, let's say you have a certain colony, right, where there are a number of different phones, right, or units, right, and they have a restriction on the number of channels, right, that they can utilize, right? So earlier they used to have this operator system where they would plug in some line and not the others, and so on and so forth, right? Now you can have a similar generalization of that, right, in terms of the high throughput or high efficiency throughput of a certain number of nodes, right, and a shared channel, or a few shared channels, right? So it turns out that if you were to have entanglement, right, you can possibly do this idea of a network recovery. So let's say the network fails, right? There is a node that stops working, right? Can you utilize entanglement to find a network recovery scheme or protocol, right? And that is what is called as multi-node failure that you can address using entanglement, right? So this was something we had been looking at for what is known as the higher order butterfly network in the classical domain, right? So this is just the scheme for that. So there is a certain manner in which quantum non-demolition measurements, which is that the measurement does not quite affect the state of the system, and there are ways to do that, right? In general, it does, but in certain cases, it doesn't. If you were to fine tune and engineer it in a certain way, and that can be utilized for recovery of nodes when some of the nodes, for instance, fail, or rather recovery of the network when some of the nodes fail, right? So I've just shown that here, and I'll be happy to discuss that with anyone who may be interested to, and may raise that in the questions as well. I'll be happy to discuss this further. Okay, and then finally, we have the idea of quantum walks, right? And this idea that you all may have seen this process of the Monte Carlo method, right? What does it mean? You have a certain kind of probability of, let's say, 2 or more options for a certain experiment, right? A simple example would be that of a person walking, right? And the probability of the person going to the right or to the left, right, being defined in a certain manner. And us being asked, what is the probability, or what is the likelihood of finding them in, let's say, 5 steps to the right after a certain number of steps taken, right? So there is a certain idea of the random walk, right? And there is an analog in the quantum domain called the quantum random walk, right? So one can utilize the quantum random walk and also generate hyperentanglement, right? And that can be done using what is known as the cascaded circuitry. So I'll just quickly go on to that. The cascaded circuitry is given as herewith, right? You have this idea that you see there are different kinds of points where the light, this is, so the system here being considered is light, right? And there are these blue boxes that you see, right? That is the point where the light channels are being moving in one direction or the other. That is basically what is called the polarization beam splitter, right? The idea that dependent on the polarization of the state, you have basically the movement into one or the other channel, right? And you can see that just like in the previous one of the slides, there is a selective manipulation of one of the channels, right? In this case, there is an electro-optic modulator, which looks at the frequency modulation, right? And there is a compensating half-wave plate as well, which is put in both the channels. So the idea is that using this circuitry, you can have a hyper entanglement over polarization, path, and frequency, right? And there is a manner in which it can be undertaken such that you can find this big resource state, right, at the very end, where you see these small semicircular gray bits, right? These are the detectors. So you can utilize that to find what are the correlation patterns that you develop after the entire system has been undertaken or thing has been undertaken. Now, this is a characterization of the entanglement, right, which saw in different in these the combination of degrees of freedom, right? So you have polarization, frequency, and path, right? So there are different kinds of characterizations I had described. One is called negativity, right? Interestingly, it's a very strange word to use, but there is a reason for that. There's a definition which has an implication on the terminology as well. So the negativity is utilized for characterizing this. And then you can also have a probability distribution of the different positions. And so you see here, there is a very interesting point I would like to quickly mention. In a random walk in the classical domain, there is a certain centralization around a central point, right? So you, for instance, around the 0 point, you will find a peak, right, of sorts, or rather a higher concentration in that place. Whereas in the quantum random walk, there is a certain dissipative aspect, right? There is a certain movement to the fringes, so to say, right? And you see the centralization around the points on the far ends of that distribution. And the theta here that you see is basically when you have the random walk defined in terms of the in terms of the elements that we have out here, right? So the walk evolution is done using what is known as this quantum coin operation, right? So the quantum coin operation has a certain parameter theta, and that is what is varied here to find the different kinds of characterization that we have seen, right? So now, before I close and we start open for discussions, all of this is very good, right? We are all talking about quantum correlations, entanglement in multiple degrees of freedom. But the key point here is how to protect the state, right? How to correct for errors, right? And that is what we really need to focus on going forward, because quantum error correction and mitigation is of prime importance if we have to have a viable kind of system that can do computation at a big scale, right? So this has been one of the recent works or recent forays of sorts. And the idea here is that entanglement and the states we are using, right, they are what are known as noisy intermediate scale quantum computing systems, NISQ, right? NISQ. And you can see this graph in the middle graph out here. And what it shows you is the number of physical qubits, right? So at the moment, we are somewhere in the 70 to 80 qubit mark, right? In the IBM systems and so on. And within 5 years, we would like to reach somewhere around the 1,000 physical qubit mark, which is a fairly ambitious plan, but it can possibly be done, right? And this entire regime is called as the noisy intermediate scale quantum computing regime, right? So it's intermediate because it's not very, very large, right? In certain senses, I mean, logical sense of sorts, and noisy because there is a certain noise aspect to it, right? And if we were to go beyond that, that is what we call as fault tolerant quantum computing, right? When you have large number of qubits, right? 10,000, 1 lakh, right? And so on. That's a huge target to take, right? And then there are certain thresholds of error correction that we need to account for, right? So now when we are talking about quantum systems or quantum computing systems, there are two different layers, right? The physical layer and the logical layer, right? And the idea is that the physical layer has the physical systems, right? The controls, the qubit themselves, a manner of detecting, measuring, readout of the variables, right? And then you have the error correction based on that, right? And then you have the logical bits going on, the software, right? The software side of things, right? Where the algorithms kind of operate and so on and so forth, right? So now the idea is that quantum channel, right, usually is what is known as a CPTP map, right? This is a mathematical term. You don't have to worry about much on that. But the idea is that there is a certain kind of trace preserving nature that is accounted for, but that is not generally the case, right? That's the ideal case when you have the trace preserving aspect. But in general, the system, as I was talking about, has a correlation with its environment, right? And because of the correlation with its environment, that the whole system is that evolution is no longer unitary, and we cannot describe it using a trace preserving linear map, so to say, right? So there is what is known as a loss of coherence, right? Decoherence, as we talk about often, right? And that has to be accounted for. So just to give you a context, a little bit of context of a real system, in superconducting qubits, right, we have had a number of different platforms or aspects or kinds of qubits we have utilized. There's something called the transmon qubit, right, and something known as a fluxonium qubit, right. These are just superconducting qubits. And over the years, you can see from 2000, before 2000 to 2016, right, you have different kinds of qubit lifetimes, right? So qubit lifetimes have increased, and operations per error, right? So if I were to take number of qubits and the operations I can do per unit of the error, that is also increasing over time, right? So in India, for instance, we have a team in TIFR under Professor Vijay Raghavan who has been looking at fluxonium qubits, right? And we are trying to develop that further. So you can see that over time, there is different trade-offs between the lifetime and operations. But the key point here is that the error correction and decoherence errors have to be minimized and reduced, right? And fluxonium qubits, actually, I've mentioned briefly on the right-hand side, have some characteristics that are very helpful. And one of them is that it's less susceptible to decoherence errors, right? So it's an important point to consider. Okay. And so now, if you were to talk about the qubits that are currently available to us, right? I had shown you different systems, right? Superconductors, ion traps, solid state qubits, quantum dots, and so on. Each of them has a certain coherence time, right? A coherence time. And it also has a certain aspect of how long it takes to may have one qubit gate or a two qubit gate, right? The time required to undertake such operations, and also the probability likelihood of how well the qubit gate is undertaken, right? So one or two qubit gates. And so for each of the systems, you can see the latest information on the different kinds of these parameters for the different kinds of quantum systems, right? So ion traps have a certain longer time and so on and so forth. And there are other trade-offs as well, right? So over time, we have seen that here we are going towards increasing complexity, right? So we are going towards places where we want to ideally go towards fault-tolerant quantum computation, right? Where there are, for the entire system is tolerant to all kinds of faults or errors as such, right? And there are ways in which we can do that using multiple logical qubits. There are algorithms for that, right? And at the moment, we have systems today. You see on the right-hand side, there is this graph with the blue bit showing us the systems today, right? And there are some codes, right, which logically or theoretically can have certain kinds of logical errors, right? And the number of physical qubits required for it, right? So we are not there all as yet, right? But we are going in that direction. And you will also see that the way in which logical errors increase for different number of qubits is also nonlinear, right? So there is a certain kind of plateauing that happens for different number of qubits, right? 5 qubits, 9 qubits, 13 qubits, and so on. And so the way we correct for error correction that is done is basically to have what is known as redundancy introduction, right? What does this mean? We encode a certain logical qubit into multiple physical qubits, right? And we try to keep checking, right, with this thing called these ancillas. Ancillas are additional qubits that are used, right? We try to keep checking for the errors as we go along, right? And then we fix them also, right, with unitary transformations. So there is something known as the syndrome of the error and the correction or fixing of the error using different kinds of unitaries, right? So you have things like toric codes, right? I have just given an example there. Toric codes that are also lattice-based codes, right? Where you have a specific kind of architecture, and there are two classes of qubits or two kinds of qubits, basically. I'll not go too much into that, but this is a manner of undertaking error correction and having a robust system, more of, right? But oftentimes we can't correct for error, but we can mitigate for error, right? What does this mean? That we can reduce the noise-induced bias, right, in the expectation value of these outputs, right, when multiple runs have been done, right? So not one run, right? Instead of that, we focus on multiple runs, and in the collective sense, we try to reduce the post processing error output, right? And there are various ways to undertake error mitigation, such as error extrapolation, and then there is quasi probability decomposition, right? The idea is that if we were to take an ideal quantum circuit, right, and we make it into a bunch of noisy circuits, right, which have quasi-probabilistic mixture, as it is called, then we can approximate that. We can approximate the joint operation or the ensemble operation of those noisy circuits and try to see if the ideal noise-free quantum circuit can be brought about, right, or the ideas inherent in them, or the what we want to seek from that can be understood, right? So, and there are various other error mitigation methods, learning methods, subscales, expansions, and so on and so forth. So just one bit here. So you have this classical computer. This graph shows you there are places where you can do quantum error correction and quantum error mitigation, and there is an associated runtime to it, right? So you can see quantum error mitigation is useful because it has a much smaller runtime given quantum circuit complexity. Let's say we have a certain specific complexity. Given that, the runtime is much lesser in many of the error mitigation strategies than error correction. That is why we often go for error mitigation and not error correction. Okay, and then a few of the final slides. So there are different stages of these quantum computing aspects which have been covered. So there we started with something called the quantum annealer, right? We have now gone to certain tens of qubits, right, in different kinds of systems. These both exist. These are existing systems. Then we have what is known as a gate-based quantum computer, right? That demonstrates quantum supremacy, which means that you have a certain supremacy aspect to it, an advantage using the quantum systems over the classical ones, right? And Google's 7-qubit computer claims, right, this is still a claim of sorts, to outperform the supercomputer frontier, right, by almost 47 years, right? That's what is the claim. Then there are others which demonstrate quantum supremacy in the annealer systems, right? And so on and so forth, right? So when we go to G4, which is the final level, that's a large quantum computer with more than 1,000 qubits, right? And so this work is still going on, right? We have not even reached A3, G3, as it is called, which is basically commercially useful quantum computers. And so we are somewhere in the A2, G2B state, right? So that is where we are standing right now in the international domain, right? And so there are many companies working on this. Google is working, Microsoft, and so on. And there are error rates that each of them have had in their specific systems they're working with, right? So I've just highlighted a few of the error rates, and you can see that for the Microsoft Quantum Station Q, there is a lesser error rate, right? Because they're trying to work with some systems which have an inherent lesser error rate that can be resilient to noise, so to say, right? And so the way forward for us as a country, right, and as well as for research groups, I think, is to look at these different kinds of ways to do logical error correction, right? New methods, new codes have to be looked at, and we have to keep on looking at fabrication and the noise reduction process, right, as we go along. There are also things like AI and ML, right, artificial intelligence and machine learning, which also help in reducing the code testing time and seeing how the benchmarking can happen, right? So we need to compare the error rates of systems we are running with certain other international systems or idealistic kind of theoretical systems that we are looking at. We need to run our quantum systems or the error codes on substrates available to us and compare it with the theoretical understanding, right? And then finally, we also, of course, as a country, have to look at different kinds of quantum processors, right? And looking at a theoretical experimental synergy to better develop this going forward. I'd just like to acknowledge some of the works I have previously done. So Professor Brian Josephson, of course, more in the pure condensed matter side, and Professor Crispin Barnes in the quantum information processing aspect, right? And that is where I had looked at the condensed matter system-based approach as well. With Professor Dipankar Home and Professor Sogato Bose looking at complementarity and foundations of quantum mechanics. Professor Prashanta Panigrahi looking at quantum entanglement. Professor Shayan, he has been looking at network coding with him and optical realization as well. And some of my institutional affiliations over the years, which I have worked on. So I'll leave it at that, and I'm happy to field questions.
Uh, thank you, Professor Gopinath. Really, it's a very wonderful talk and very well structured talk. And I think 1.5 hours, you have covered most of the a corner of the quantum mechanics is application and implementation. And now, if you allow me to, then you can put some questions on your dashboard.
Yeah, yeah.
So I'm
I'll
putting
just
it on your
see.
dashboard.
Yeah.
Please show it.
Okay. Is quantum
Yeah.
entanglement occur between more than two particles? If yes, then what's the effect of second part different particle on third particle? Okay. So multipartite entanglement, right? I was showing you the 7 qubit state that has entanglement across different number of qubits. There are 7 qubits in that case, and there is an entanglement across these qubits, right? Now, there is a debate going on as to characterization of multipartite entanglement, but there's definitely non-zero, non-trivial entanglement in more than two particles as well, right? As for the second question, if yes, then what's the effect? So I was talking about entanglement monogamy. The idea here is that there is a trade-off in terms of introducing further systems and having developing correlations with these newer systems on the old ones, right? So there will definitely be a certain kind of impact of sorts, right? But it may reduce basically, right, in a certain manner of speaking. And also there's a noise factor also. When you try to introduce further qubits, there'll be noise factor that comes in as well. So one has to account for those and then engineer the system very well, basically. Yeah.
Okay. Now the second question, I'm just putting it.
Okay, why quantum particle only exist in certain allowed energy levels? Why this universe allow the quantizer? Very, very nice. Well, this is an actually this is something which is I wouldn't say axiomatic, right? But there is an aspect that comes from experimentation, right? So when we were talking about different kinds of radiations, right, the radiation picture was where Max Planck and various others were working on. And given so physics or any theory, right, has to describe what is seen in empirical data, right? And it was seen that there are some things like ultraviolet catastrophe. There are various problems that come when we look at the wave-like nature or the conventional classical optical side of things, and whereas or radiation side of things. Whereas in the sense of the quantum world, we see that only when we look at packets of energy, right, then we get the results that we are seeing in the experiments, right? We find that there is a nature follows that, right? Nature is inherently that in those particular regimes and systems, right? So that is why we kind of go ahead with it. Now, what you're asking in the second bit is a very fundamental metaphysical question almost, right? Why is nature allowing for this, right? Now, the thing is, nature is allowing for it if you were to take it in a certain domain, right? In the sense that if you were to, let's say, coarse grain, right? You were to move out from the minute to the one to the outside world, right? There you will still see that classical mechanics still applies, right? You can see that gravity, the laws of gravity that we know of, right, or the laws of mechanics, right, the rolling ball, for instance, right, we still have a certain classicality that can be still ascribed to it, right? So my answer to that would be that there are different theories, right, and even Stephen Hawking talks about this, which are applicable in different regimes of nature, right? And it just so happens that in that minutest of levels, some of the scale levels, you have the quantization that is seen, right? But in certain different regimes, quantization is not often seen or required, right? So in the classical domain, we don't require quantum mechanics per se, right? So I would, I mean, respond to that in that manner. Yeah.
Thank you. Thank you. Now the
Yes, very,
another
very,
question is
very good
asked.
question. That's a very good question. Does quantum entanglement violate Einstein's special relativity? Right? No, it does not. Right? Because the thing is, so Einstein's relativity, what does this say? Right? It says that a physical system, right, cannot move faster than the speed of light, right? Or it will have a certain kind of accretion of mass, for instance, as it approaches the speed of light, right? Now, the thing is, in entanglement, when we're talking about teleportation, right, when you are moving this the state of this particle immediately to the other one, right, you will notice that in that scheme there was a place where I had shown unitary transformation, right? Now you may have the transfer of information instantaneously, right, immediately, right? But that is not necessarily useful information, right? Physically useful information. For making it physically useful or useful, you have to undertake certain kinds of transformations, right? Now if you were to account for the time taken for the teleportation and the transformations, right, then that does not violate relativity, right? Because that net time is effectively more than the time taken by light to move from that one place to the other. right? So you could say that because at the level of information, relativity has no constraint on that, right? Einstein didn't say that information can't travel faster than the speed of light, right? Einstein just said that physical objects, right, physical entities, right, there is a constraint on that, right? And in this case there's a constraint on the useful information that is inherent in entanglement or in teleportation, right? So therefore it doesn't quite violate relativity.
Okay. The another question from the same guy, Professor Goa. Actually, we should, I think, have a separate session for such kind of a questions that you are very keen to interferences between the spirituality and the quantum mechanics. You know, you get the answer of this question.
This is from the human, humanities, or maybe the emotional side of things. Sure. Is it true that emotional connection between people who are in love is because of entanglement? Can be proven using this? So um, unfortunately, physics cannot give you the answer for that, right? Because we yet, I would say, maybe at some point we'll find that emotions and mind, right, has a certain quantum side to it, or brains. There is Penrose. Roger Penrose has given some ideas. Obviously, there's debate and controversy around it as well. But how consciousness comes from entanglement, or at least a quantum picture, right? So whether emotions come from that is a question that has still not been addressed or even brought forth. But you can, in a slightly higher metaphysical way, say that it is an interconnectedness, right, which is present and seen in entanglement. And of course, when you have emotional connect, then you also have that kind of a connection as well.
Thank you. And I would like to share one information to our audience that Professor Goa has very keen interest to, how to interconnect the spirituality with quantum mechanics. Definitely we'll have a another session for such kind of stuff.
Yeah,
Thank you,
but
Professor Goa. And
Ashish ji, we have to be very careful, because sometimes we cannot just connect. We can just see the resonances, right? The resonances maybe,
yeah,
but
yes,
the connecting
definitely.
is dangerous, because there is this clear kind of, yeah.
Yeah. Thank you, Professor Goha. And I think I would like to, want your take on as a being a faculty of the physics, and as we can see, in the higher education, students generally used to take quantum mechanics as a serious concern. But we can see in the undergraduate and the school level students when they encounter first come with the face of quantum mechanics during
Yeah,
their ninth standard when they face with the quantum numbers. But it is very
right.
difficult as a faculty that how we can appeal their imagination on that particular level. Even I would like to take your take on that aspect.
So on the concept of quantum numbers.
Yeah, yeah. Actually, during the school days, now the students are facing first time they encountered with the quantum world when they used to write quantum number. At that time, we how the teachers should appeal their imagination toward the vast area of the quantum mechanics, because
Oh, okay, right, right.
during the school times, students get kind of phobia when they see the quantum numbers, quantum mechanics, whatever.
Yes, yes. So I think the way to do it, actually, myself, I would say that the way physics works itself, right, or science works, right, is that you see discontinuities in your phenomena, or rather the experimentation and the theory that is available. So I always like to kind of contextualize the study of quantum mechanics, right? As in, why was it that quantum mechanics had to even come into being, right? And there were some fundamental experiments, fundamental questions, right, which were asked, be it in radiation or be it elsewhere. And it was only after that was addressed and it was seen that theory was not sufficient, right, that these numbers were brought in, right? So people often ask, for instance, what is the quantum spin? Is it actually a spin of a ball, like a spin of a ball, right? It's of course not, right? There is a certain not it can be visualized per se, right? Similarly, if you were to talk about the probabilistic nature, if I say that, let's say, the table that my laptop is on is red and black and blue and brown at the same time, right? What does that even mean, right? So it is very, very important to highlight that nature at its most fundamental is often not classically intuitive, right? It's not classically intuitive in the sense that there is a certain divide between what we see around us, right, and the functioning at that minute level, right? So this whole idea of that we can visualize things, right, may not always be applicable, right? So there are different ways. Contextualization, clarity of concept, right, and this divide of sorts, right, the Bohr boundary as we call it, and certain other applications, I think this is the way in which quantum mechanics can be introduced,
Yeah.
right? Because then students are truly fascinated by why, why this shift came, right, and what does it mean to have this shift in the world of science and physics. Yeah.
Okay. Thank you. Absolutely. You are all you have given all the right answers regarding the queries. And one thing I wanted to ask that how far you can see the quantum entanglement and the theory and its application for the industrial users. As you can see that this most of the challenges can be solved out with the quantum entanglement, quantum computing, as cyber security or and other challenges which we are facing in the society. How far you can see
Yeah.
how these aspects can solve the
So
societal problem.
yeah, so I think we are still not there, I would say, because I showed you the level G4, right? G3, G4 in my
Yeah.
that table. We have not reached there in terms of the number of qubits we can generate. One of the big problems we have in quantum computing is that of decoherence, right? And the delicate nature of the quantum states, right? So to utilize a number of different systems, it is very difficult to do it in the current existing kind of platforms, right? So ideally, yes, we could be doing it. For instance, nowadays, actually, my viewers will be the viewers here will be happy to know that you have publicly available platforms, right, like IBM Quantum Experience, and there is this language called Qiskit, or rather a package which is called Qiskit, right, Qiskit, where you can do quantum computation tasks, right, or you can run certain kinds of algorithms and protocols on that, and it is basically directed or scheduled on IBM system, which is an actual quantum computing system, right? So there are ways in which it can be done, but the larger problems, right? We still need a little more development on the experimental and realization front before we can make it market, viable as well as on a large scale, right? So that is, we are still not there as such.
Thank you, Professor. And I think you have answered all most of the queries, and really we are delighted to after your talk, and it's a very structured, wonderful talk. Your time, which you have taken for us, and definitely we would like to request you that whenever you get time, definitely we want to meet you in a person on our campus. Okay, so you can interact with our young students definitely. And I think let me conclude, dear friends, with quote Anubhadra Kritavo Yanto Vishyataha, which means uh, let the knowledge from all across the directions, and definitely we have to tune up with receiving that kind of a knowledge. And we are here to bring all intellectuals from across the globe for our audience, and especially through the Gyan Setu platform. So now we are signing off until we meet again. Thank you, Professor Gram.
Thank you.